my name is VAISHNAVI, daughter of PRABAHKARAN. My matrix number is F25A1910. Today, I will be presenting my project titled Visualizing Post-Harvest Respiration Rates in Malaysian Oil Palm Fresh Fruit Branches During Derivatives. So, this project demonstrates how derivatives can be used to analyze changes in glucose concentration after oil palm fruits are harvested. Through an interactive website, users can visualize how glucose decreases over time and understand its impact on oil quality. The first section explains the biological problem faced by Malaysia's palm oil industry. Once a fresh fruit branch or FFT is harvested, its cells remain alive and continue undergoing respiration. During respiration, stored glucose is consumed to produce energy. At the same time, carbon dioxide and heat are released. As glucose continues to be depleted, the fruit begins to deteriorate. This can lead to weight loss and the breakdown of lipids into free fatty acids, which lowers the oil quality. Therefore, monitoring the rate at which glucose is depleted is important for determining the best processing time. So, next we have the interactive Spoilix curve. This graph shows how glucose concentrates changes over a period of 48 hours after harvesting. The horizontal axis represents time in hours after harvest. The vertical axis represents glucose concentration in milligrams per gram. As we can see, the curve continuously decreases over time. It indicates that glucose is gradually being consumed through the respiration. So, to model this process mathematically, we use an exponentiated decay function. The glucose concentration is represented by S hours after harvested. Fx represents the amount of glucose remaining. 150 milligram per gram is initial glucose concentration and 0.04 is the decay constant. This equation predicts how much glucose remains at any given time after harvesting. Using the derivatives to determine how quickly glucose is being depleted, we differentiate the function. This derivative represents the instantaneous rate of glucose depletion. The negative signs tell us that glucose concentration is decreasing over time. The derivative was obtained using the chain rule and allows us to measure how fast glucose is being consumed at any specific hour. So one of the key features of my website is the calculated derivative matrix section. The point on the graph is selected, and the selected time, the time remaining glucose concentration, and the depletion rate. For example, at 16 hours after harvest, glucose remaining glucose is at 79.09 mg. The depletion rate is approximately negative 3.43 milligram. This means glucose is still decreasing, but not rapidly as it was immediately after harvesting. This website also translates mathematical results into practical agricultural insights. At around 14 hours post-harvest, the depletion speed has slowed because easily accessible sugars are becoming depleted. However, this also signals that the possibility of further deterioration process that may affect oil quality. This information can help factory managers decide when fruits should be harvested or processed to minimize losses and maintain product quality. In conclusion, my project demonstrates how derivatives can be applied to a real agricultural problem. Using an exponential decay model and its derivative, we can predict both the amount of glucose remaining and the rate at which it is being depleted after harvest. The interactive website helps users visualize these changes and understand how mathematics can support decision-making in agriculture. This project shows that calculus is not only a classroom concept, but also a valuable tool for improving efficiency and maintaining quality in Malaysia's palm oil industry. Thank you.
Assalamualaikum and good evening, everyone. My name is Mama AIMAN bin KHAMIS, metric F45A2054, and I am an undergraduate student in the Food Security Program. The bioscience problem centered in this project is the optimization of crop yield through the mathematical modeling of biomass growth rates. Specifically, we focus on the high yield Malaysia rice variety over its standard 120-day cropping cycle. Using historical data from RD, we track the accumulated dry matter biomass donated as FT in gram per square meter using a logistic growth curve. The true physiological breakthrough comes when we compute the first derivative, which gives us the crop growth rate. The core challenge is pinpointing the exact inflection day where growth velocity peaks, so we know when the plant demands the most nutrients. I studying this critical because it boils down to national food security and resources efficiency. Under Malaysia National Agro-Food Policy 2.0, the country aims for a 75% to 80% self-sufficiency level for rice. To reach this target without wasting resources, farmers cannot rely on guesswork. By analyzing the derivative, we discover the precise moment of clinical initiation, the phase where the crop metabolism accelerates to its absolute peak. Applying top-dressing nitrogen fertilizers exactly at this mathematical threshold maximize nutrient absorption, increase grain density, reduce fertilizer runoff waste, and ultimately secure higher crop yields to feed the nation. So the graph is, let's look how the plant behave across its 120 days cycle using our interactive simulator dashboard. We can break this down into 5 key growth phase based on the derivative value. First, early sowing and tailoring. Days 0 to 24. In this initial phase, total biomass is low and the crop growth rate is flatlining around 0.5 to 4.0 grams per square meter per day. The plant is prioritizing underground root stabilization of visible weight grade. The agronomic directive here is to maintain shallow flooding to stimulate early stem production. Next is active tailoring acceleration, days 35 to 51. Growth velocity climbs rapidly as solar absorption optimizes. This is the time to apply primary urea to feed active stem division. Next is peak growth, days 52 to 71. This is the inflection point at day 60. Growth velocity hits its absolute peak. Applying fertilizer exactly here maximize final seed count and grain size. Next is flowering and grain filling from day 72 to 94. At this stage, the derivative begins to slow down because the energy shifting from the level to filling the grain hits with stretch. High water level must be maintained here to support grain moisture demands. Next, lastly is grain ripening and field drying, days 95 to 120. Finally, as we approach day 120, growth is completely suspended and the growth rate dropped to near zero. The plant has reached its carrying capacity. The field drained 10 days before harvest to allow mechanized harvest into dry soil. To conclude, while the simulator successfully demonstrates the relationship between calculus and crop physiology, I would like to recommend one key improvement to make this HTML tool even better, which is integrating a real-time weather factor. Currently, parameters like the growth index and maximum biomass are adjusted manually via static drop-down menus. By integrating a live weather, the simulator could automatically ingest real-time local data, such as average daily temperature and solar radiation level in regions like the Muda irrigation area. Because the temperature directly dictates metabolic rates, this adjustment would dynamically shift the infection day, providing real-time, hyper-localized fertilizer alerts for precision farming right on the web page. Okay, that's all from me. Thank you.
Hi, Assalamualaikum and good evening. I'm NORSYAMIRA binti Rahim. My matrix number F25A1851. I'm from course Food Security. So today I want to talk about the Bioscience Challenge. Why I choose this title? Because boost food security. First, for boost food security, it's focused on maximizing the yield of Malaysia. Our 297, it's focus of rice variety to help the nation become self-sufficient. Second, Fortin smart into farming solutions. It proves calculus isn't just a theory. Using the first derivative, f prime of x, find the exact date plants need fertilizer loss. Third, for prevents waste and risk. It helps farmers avoid under-fertilizing standard crops or over-fertilizing, which is causes crop to fall over and invite pests. The core bioscience challenge here is precision timing for nitrogen fertilization in the MR297 paddy variety. To maximize yield and safeguard national food security, fertilizer must be applied exactly during the peak vegetative phase. Apply it too early and nutrient wash away. Apply it too late and grain development is primarily stunted. Therefore, we need calculus to track daily growth velocity rather than just guessing based on physical crop height. Why is tracking this growth velocity so critical? First, using the first derivative f prime of x, research can monitor how environmental stress, like drought or disease, affect crop development in real time. Second, it's optimized water management. Farmers can conserve water when growth is low, but ensure ideal digs during peak growth windows. That it prevents pests. Vulnerabilities over fertilization speaks growth velocity and sustainability, creating soft hollow stalk that become easy target for pests like the brown penhopper. Let's look at how this interactive platform operates. Three Bioscience scenario A simulates optimal Mardi condition with a maximum height L of 110 cm. Scenario B models tented growth for nutrient deficiency, while scenario C once or several crop logging risk due to excess nitrogen. Calculus made Bioscience the function fx model physical height over the 150-day cycle. The first derivative f of prime x gives the instantaneous growth rates in centimeters per day. On day 50, the second derivative fx equals 0, marking the inflection point where the plant hits its absolute maximum growth speed. The life calculator, when we drag the cylinder to day 50, panicle intonation space, this system shows a peak rate of 2.2 cm per day. The system immediately triggers the agronomic advisory. Second, nitrogen top dressing requirement. 80 kg per HA of NPK fertilizer need to the crop its moment of maximum metabolic demands. To improve HTML structure and user experience, I recommend integrating a dynamic dashboard alerts banner. Using HTML5 dialog elements at the top of the page, currently, the interactive graph and the advisor text are separated by a long scroll. A dynamic alert system that changes color instantly. Live flashing crimson red for the scenario C, logging risk, would give farmers immediate visual feedback without making them dig through text blocks. In conclusion, the PADI CALCSFM project proves that calculus is not just the theoretical equation on a whiteboard. It's a practical agriculture bioscience tool capable of safeguarding our food security. Thank you very much for your time.
Assalamualaikum and good evening, everyone. My name is ALIEYA. Message number F25D1949. Today, I would like to present my project titled on FFV post-harvest respiratory analysis. In this project, I developed a website that focuses on analyzing respiration data of palm oil fresh fruit bunches or FFB after harvesting. The most important part of this project is not the website itself, but the data analysis performance using the website. The data used in this study focus on carbon dioxide or CO2 production during the post-harvest period after harvesting. Oil palm fruit bunches remain biologically active and continue to respire. During respiration, oxygen is consumed while carbon dioxide is released. Therefore, measuring CO2 production allows us to evaluate the respiration activity of the fruit. For this analysis, cumulative CO2 production data was collected over a period of time. This value represents the total amount of carbon dioxide released by the fruit bunches during storage. As time increased, the cumulative CO2 value also increased because respiration continuously occurs. However, raw cumulative CO2 data alone does not clearly show how respiration changed over time. It only shows the total carbon dioxide produced. Therefore, further analysis is required to determine the actual respiration rate. To solve this problem, the data was entered into the website. The website used the computer's mathematical model to fit the cumulative CO production data. This model is notable because biological respiration process often follow a non-linear pattern. The Gomez curve describes how carbon dioxide production changed throughout the post-harvest period. After fitting the data, the website calculates the derivative of the Gomez function. The derivative represents the respiration rate at different time points. This is important because of the respiration rate provide more detailed information about the metabolic activity of the fruit bunches. From the analysis data, I was able to observe the respiration behavior of the oil palm fruit bunches over time. The results show how respiration activity shifts during the post-harvest period. The generative curve makes it easier to identify periods where respiration activity increases. Reaches the maximum point and gradually decreases. The website also generates graphical output that allow the data to be visualized more clearly instead of analyzing long tables of numbering value. The graph provide a clear representation of the respiration pattern. This made interpretation of the data much easier. Another important parameter option the analysis was the maximum respiration rate. This value indicates the higher metabolic activity achieved by fruit bunches during the observed period. By analyzing this value, we can better understand the physiological condition of the harvest fruit. The cumulative CO2 production data also provide information about the overall respiration process. Higher cumulation CO2 value indicate great respiratory activity, while changes in the slope of the curve reflection differ in respiratory rates through storage. Normally, fitting experimental data of the Gomez model and calculate the derivative require several mathematical steps. Performing this calculation manually can be time-consuming and may lead to error. However, the website processes the data instantly and produces accurate results. The automatic analysis also improves constantly because every data is processed using the same mathematical method. This reduces human error and increases durability of the result obtained from the study. Overall, data analysis in this project provides important information about post-harvest respiration in oil palm fresh fruit bunches by study cumulative CO2 production as respiration rate. You can be better understand the metabolic behavior of the fruit after harvesting. In conclusion, this project demonstrates how respiration data can be analyzed efficiently using mathematical modeling and website technology. The website successfully covered the accumulation CO2 production data into respiration rate information, allowing clearer understanding of post-harvest respiration behavior in palm oil bunches. Thank you.
Black and yellow, yeah. You know what it is.